This is
It's going.
It's
Okay.
for that.
the grade wasn't stringent. This is stringent. I mean, the grade was wrong.
Hi everybody, welcome back to Experimental Math. Today we have Shashank Kanade, who will be talking to us about searching for modular companions.
Okay, thank you so much for having me. I'm going to be talking about Q series, and I'm going to be extremely rude and put Q to be a number at some point. So we'll see when we get to that. Right, so this is mainly about partitions, at least to begin with. So what are partitions? We'll take a number and write it in terms of positive numbers, and order doesn't matter. I usually write it in increasing order. Okay, so you count out the number of ways of doing such arrangements, and that's called a partition. So the main protagonist is going to be things which are identities of the following sort. They are called Rogers-Ramanujan type identities. So let me tell you what are Rogers-Ramanujan identities. So take a number, integer, then the number of ways. So this is a pair of identities. I'll tell you one, the second one is very similar. Fix a number, any number, positive integer. Then the number of partitions of n into number of partitions in which adjacent parts differ by at least 2. Tell you what that means. Is the same as the number of partitions of the same number n in which every part is congruent to either plus or minus 1 mod 5. Okay. So on one hand you have just count all the partitions in which adjacent parts differ by at least 2, and the number of such partitions is the same as the number of some other class of partitions. Okay. The second identity is very similar looking, so I'll just tell you where the difference is. You have the same condition here, that parts differ by at least 2. Okay, ditto. Additionally, smallest part is bigger than or equal to 2. So in other words, 1 is not allowed to be a part. Okay, so that's just one more condition tacked onto this. And the equality, it's number of partitions in which every part is congruent to. Now in place of plus or minus 1, you get plus or minus 2 mod 5. So very small difference on the left hand side causes quite a bit of difference on the right hand side. There are many proofs of these identities. Many of them are elementary in a way, but it's very mysterious, these identities. There is no 5 on the left hand side, but there is a very prominent 5 on the right hand side, for example. Right? Okay, so what's an example? I'll tell you an example of the first identity. So take n equal to 9, for example. Let's write down partitions in which adjacent parts differ by at least 2. So here there is only one part, so nothing to think about. Or I can write it as 8 plus 1, or I can write it as 7 plus 2, or I can write it as 6 plus 3, all are good. Or finally I can write it as 5 plus 3 plus 1. Everything is good because adjacent parts differ by at least 2. Something like 5 plus 4 is not allowed, of course, because here adjacent parts differ by 1. Something like 3 plus 3 plus 3 would not be allowed. Okay? And on the right hand side, let's write down partitions in which each part leaves remainder either 1 or 4 mod 5. So that's 9, or 6 plus 1 plus 1 plus 1, or it can be 4 plus 4 plus 1, or it can be 4 plus 1 plus, well, all ones and then all ones. And there are 5 ways to write it this way, 5 ways to write it this way. And that's the theorem for n equal to 9. Okay? any questions so far? Okay, let's write down generating functions. This is where Q comes in. Alright, so there are two things. So the generating functions are going to look different on the left hand side and right hand side. Right? Let me first write down the one for the right hand side, it's easier. It looks like, so Q is for now a formal variable. I'll tell you when we will write it down as a number. Right, so these are all the numbers. The exponents are 1, 4, 6. They are the ones that leave remainder. 1 or 4, 1 or 5. Okay? So that's the right hand side generating function. Okay? The left hand side generating function, okay, let me write, this is for RHS. For the LHS, this is for the first identity. This is this is the generating function for the LHS. Okay. Whenever I write down something like 1 over 1 minus q, you're supposed to expand it in a geometric series. So, okay. Okay. So again, it's not too difficult to know that the generating function of partitions where adjacent parts differ by at least 2 is this. You still need to think about it at least a little bit. Okay, there are still a couple of steps, and it's all elementary, but you'll need to think a little bit. It's not as immediate as just this. Okay. All right. So. And of course, the equality here is the Ramanujan identity 1. Okay? So that equality is the same as the equality there. Alright, so let me introduce some words or some terminology that is relevant for us. So this here, this thing, is q to the n squared divided by all that. This is called analytic sum side, or I will call it analytic sum side. I don't really know which is the prevalent term. I think this is quite prevalent. We'll call it analytic. Although I'm not doing any analysis right now, I'll still call it analytic sum side. Okay. This is, of course, the product side. Yeah. And okay, as I said, the product side is very easily the same as the congruence conditions. So these are called the congruence conditions. Congruence conditions. Okay. And on the left hand side here, what I have, I'll just call them difference conditions. Okay. Now we have 4 things here. Right? And let me tell you in general how it goes. So you have these difference conditions. You have analytic sum sides, which are natural generating functions for the difference conditions. And on the other hand, you have product sides. Okay? Product sides are usually very easily the generating functions of the congruence conditions. Getting from here to here or here to here is typically very hard, proving any of these equalities. So both of these arrows are typically hard problems. There's a tiny bit of advantage here sometimes, tiny bit of advantage here sometimes. If you have analytic sum sides, you can conceive of using some hypergeometric summation techniques or whatever to get here. But sometimes the difference conditions tell you immediately what the recursions are, and that sometimes helps. But on the whole, this side is it lives in a different world than this side. Okay. Now here, it is again many times quite difficult. Not as hard as going from here to here, but many times quite difficult. So I'll tell you one example of this. In Ramanujan, you still need to think, it's quite immediate, 2 lines you'll get it. But in general it might be hard. So this is the game. There are many identities of that Ramanujan kind. I'll show you some. And some of them are conjectures still. I'll mention some conjectures for which this side is known, but there is a conjecture for the product side and we don't know if they are known. Alright, so let me mention a few conjectures which will feature. So these conjectures are by myself and Matthew Russell. These were on arXiv in 2014, so I'll mention one of them. Matthew has one companion conjecture in his thesis on this. Okay, so same style. So number of partitions of n is again a positive integer, where difference, so there are a bunch of conditions, is bigger than or equal to 3 at distance 2. I'll explain what that means. Okay, and if consecutive parts differ by 0 or 1, then their sum is divisible by 3. Okay, so something like 3 plus 4 is not allowed to appear, because 3 plus 4, they differ by 1, but 3 plus 4 is 7, that's not divisible by 3. So you're not allowed to have 3 plus 4 anywhere in your partition. What does this mean? This means that if you write your partition as, let's say, something like that, okay? Anytime you jump over 2 plus signs, you should get a part that is at least 3 higher than what you started. Anytime you jump over 2 plus signs, okay? So instead of adjacent parts there, here the condition is about parts at a distance. Yeah. Okay, so this is the sum side, or the difference conditions, okay? And this is the same as the number of partitions of the same n, in which each part is congruent to plus or minus 1 or plus or minus 3 mod 9. Okay, so that mod 5 is now changed to mod 9. Okay. Again, there is 3 on the left hand side, but there is no 9, and there is no reason why it should be anything here. Okay. Alright, so these are conjectures. They have been checked until partitions of whatever you want, like 1500 or something. There's no doubt in anyone's mind that about their truth. They have to be true, but still it's not proved yet. Okay? Now let me point out something that is important already. So here you see that if one congruence class is allowed, I say congruent to 1, then I'm also allowing minus 1. Okay. Same in there, if you see it is plus or minus 1 mod 3 plus or minus 3 mod 9. So these are called symmetric products. Right, so there are 2 more symmetric conjectures. There are 2 more asymmetric conjectures, all mod 9. They have a little variation on the sum side, a little variation on the product side, but just like there are 2 Ramanujan, there are in total 5 of these. Okay? In our original paper, we had 4 of these in there, and then Matthew in his thesis had the 5th one. Okay. So now, as I said, sometimes, so I've given you a conjecture that says difference conditions are the same as congruence conditions, and congruence conditions product size is easy to go. So in this case, it was quite hard to get analytic sum size. Okay, so last year, Kursungoz, he figured out the analytic sum size for the difference conditions, and it's so easy, deceptively easy looking, but it's very, very involved. So this was in 18, it might have been 19, but anyway, I forget exactly. So on the left hand side you get, now it's a double sum, n squared plus 3 and m plus 3m squared. It was last year. Anyway. Okay, so I'll introduce these symbols. I have not told you what they are. And of course the product side is easy. It is q, q cube, q to the 6, q to the 8, and period is q to the 9, infinity. Okay, so I'll tell you what these things mean. Okay, so these are called Kokomo symbols. So A, Q, T. Okay, this is just the product 1 minus A, 1 minus A cube, all the way up to 1 minus A to the Q with T minus 1. If you put an infinity there, then you just keep going, like here. And now, okay, there is a semicolon here which you probably can't see very well. These are semicolons. So what comes after the semicolon is somewhat, it's like the period of what you're using. It's A, Q, and dot, dot, dot. So here you have a product Q, this is just a shorthand, it's Q, Q to the 9, infinity, times Q cube, Q to the 9, infinity, and so on. It's just a shorthand. Can you make sense of this? It's not important. What's important is what's written here for the product size. This is the important stuff that Kant figured out. He hasn't proved this equality, that's still a conjecture. He proved that this here is the generating function of the difference conditions. Okay. Any questions up to that? Okay. It's quite interesting and involved what he did. Okay, so let me just throw out some other names of such identities, which this is a very vast world. There are many, many, many identities of this kind. So I'll keep the Rogers-Ramanujan here. Okay. So Rogers-Ramanujan are mod 5. These are too hard, I'm keeping them aside, but there are some easier than those generalizations of these guys. So the first ones to be found, to my knowledge, is the Gordon-Andrews identities. So these are odd modulus generalizations in place of that mod 5, and then you have a different condition on the different condition side. I think before this there might have been a Schur, I think this was definitely earlier, Schur's mod 6 identities, but they don't fit into this family. The Gordon-Andrews and Rogers-Ramanujan, they fit into a nice family. Then there is an even modular generalization that is Andrews pursuit. These are called even moduli. And then there is Caparelli's identities. These are not in this family, but they are very, very important. These are mod 12 identities. And the reason I care about any of this is because all of these identities show up in many algebraic contexts. For example, in the representation theory, or affine algebras, and vertex operator algebras, and that was what my advisor did in late 70s. started with the work of Lebowski and Wilson. And Caparelli was their student. Okay, so there are many identities of that kind, and on the analytic sum side, they have very similar looking patterns. So, so typically the analytic sum sides look like something like this. I shouldn't have erased this, but probably you can see it in faint here. It was summation q to the n squared divided by a q factorial. Here it is n squared plus 3nm plus 3m squared. So it's a quadratic form that is coming up in the exponent. And then you have a division by Kokomo. So this is a very typical form. It is summation over a bunch of variables. Q raised to half is just for conventional. You make a vector out of all of these, and you take a symmetric positive definite matrix. Sometimes you might have a linear aberration, which I have not talked about, but instead of that quadratic form, you might have a linear term like 3n plus 5m, something like that. That's a linear form, plus some constant. Divided by Kokomo. N1. Okay, so that's what you observe. You look at a lot of identities, and the difference conditions will typically have such a shape. Okay, quadratic form and Kokomo is the bottom. Okay, so what I'm going to talk about is that, as I said, there are many mysteries about these, and the sum sides and the product sides live in completely different worlds. One of the things is that the right-hand sides, the product sides, are manifestly modular. Okay, so I'll tell you what modular means. But no one, to the best of my knowledge, has been able to prove modularity of just the sum sides without using the equality. Okay? So for example, think about Rogers-Ramanujan identities. The product sides are modular, but can you prove the modularity just for sum sides? You don't want to use the equality because that, right? You understand the problem, yeah? Okay. So that is what I'm going to concentrate on. Okay. So what is modularity? So it is what I understand of it. I have not really worked on modularity ever, but it does show up a lot in these fields. Okay. So typically speaking, modularity has to do something about functions that behave nicely under the action of the modular group, which is SL to Z. So what is SL to Z? It is just the group of matrices with integer entries of determinant 1, okay, and a modular form of weight k is a function from the upper half plane of the complex numbers that satisfies that is holomorphic. Okay. Then it has, this is the key property, f of a tau plus b divided by c tau plus b is equal. So remember, this is weight k, so it is c tau plus b raised to k f tau, where tau is in the upper half plane and the matrix ABCD is in SL to Z. And the third condition, f is holomorphic as you approach I infinity. So as you approach, I infinity is somewhere up here. Yeah. Alright, so essentially it's functions on the upper half plane that are nice analytically, and they transform in a nice way under the action of the modular group. Okay? Alright? So that's what you have, but in general, a lot of these properties are relaxed. So instead of holomorphic, sometimes you require meromorphic or other, only real analytic or something like that. I'm not a modular forms person, so I don't really know the whole spectrum of these things. But somehow the transformation under SL2Z is retained, and sometimes we need to replace, to relax the conditions to have transformations under some subgroups, typically of finite index of SL2Z, okay? Or sometimes you have transformation law that includes have what are called multiplier systems. It's not right now too relevant for us, but let me just mention that this is not the definition. There are many relaxations you can do. For example, you can have some constants coming up here depending on what matrix you choose. You can relax the analytic things a little bit. Anyway, that all is folded into the modular world. Okay? The point is, okay, and this is, you can believe me, this is true. The symmetric products can be easily, okay, detected to be modular. Okay? The symmetric products, like the one I wrote down for Ramaswamy in this mod 9, they are essentially modular. You need one factor of, you need to multiply usually by q raised to a constant term. Okay? And that constant term is very easily found out what it is. And the symmetric products are easily modular, manifestly. There's really not much there. Okay? The hard part is telling the modularity from the sum side. So out of the 5 conjectures, remember 3 were symmetric. And now the question is, besides the 3 symmetric ones, okay, are identities. Are there more such identities, more such modular identities of the same shape? Okay. So symmetric products are modular, but everything modular does not have to be a product. So I'm asking, can you tweak something on the sum side so that you still get an identity in the same family, but it may not factor into a product, but it might still be modular. It has a chance of being modular. Do you understand the question? Right? Everything that is symmetric product has to be modular, essentially. But everything modular doesn't have to be a product. So I'm sort of expanding my search space. Okay. And unfortunately, no one knows how to prove, just given the sum sides, that they are definitely modular without going to product. Remember, these are conjectures. I don't know if the sum sides equal product side. But what we can do is get necessary conditions for a sum side to be modular. We can't prove that it is modular, but we can get necessary conditions. So I'm going to explain to you what these necessary conditions are, or at least one of them. And it's a very classical story, which I only learned recently. Okay. So this is where setting Q to a number comes into play. Okay. So now what we are going to do, we can't tell if they are modular, but we will try to get conditions, necessary conditions for it to be modular. Okay, so let me tell you what that is. Okay, so here what is happening is that Q is supposed to be visualized as 2 pi I tau, where tau is in the upper half plane. Okay? So if tau is in the upper half plane, Q ends up being inside the unit disk. And if you put tau equal to I infinity, then that maps to 0. Okay? So it's the complete disk if you include the cusp I infinity. And the point is that because of modularity, you want to look at certain asymptotics. Okay? I will not explain why you want to look at these asymptotics, but I'll tell you what happens if you look at these asymptotics. What you need to do is put tau as I over 2 pi epsilon, where epsilon goes to 0 plus. So what's happening here? This 2 pi is just to get rid of that, it's just a scaling. So tau is going like that on this here. I epsilon, epsilon goes to 0 plus. So if you plug it in, you will get Q is e to the minus epsilon, right? I times I is minus 1, 2 pi cancels. And now as epsilon goes to 0 plus, if you do it a little bit, this will mean that Q goes to 1 minus, but now it's in the unit circle and it will go on the real axis. So it's moving like this. Okay? Alright? Okay. So you want to put Q to be like this, and you want to move along this line. Now if you do it, you will see that these values go to infinity. Just plug these values in the sum side, you will see that the values go to infinity. So the point is to figure out how fast they are going to infinity. The point is, on the product side, that's easy to do. It's easy to figure that out on the product side, and the reason we are doing it is to match the answers. What we get on the sum side to what we get on the product side. Okay. So what is the answer you get on the product side? So of course, if everything goes to infinity, the point is how fast does it go? In the product side, the answer is for the product. So let me take a digression. I don't really want to look at the products right now, but at the end I want to compare the answers. So for the product, the most significant or the most dominant term that you get has the shape, okay, is of the shape exponential of p times pi squared divided by 3m epsilon. There are more terms in the expansion. This is the most, remember epsilon is going to 0 plus, so this term is blowing up. Okay? What is p and m? Where p is the number of pairs of congruence classes that are allowed modulo m. Okay, so for Rogers-Ramanujan, we had plus or minus 1 mod 5, so we had one pair of congruence class allowed mod 5. The most dominant term would be exponential of one pair, so pi squared, divided by 15 epsilon. Okay? Alright, now let's see what happens on the sum side. And this is something you can do on Maple. Okay? So I'll tell you what you can do on Maple and what you still need to do afterwards. So as I said, this is going to infinity. I just want to figure out how fast it is going to infinity. So let us plug in. Let us do everything for Rogers-Ramanujan just to get practice. So remember, the sum side was q to the n squared divided by 1 minus q, and there was a product, and then final term was 1 minus q to the n. Okay? So I want to plug in q successively going closer to 1. So what I will do is I'll pick some values for q, and I will plot really something you can quickly do on paper. I will plug in, let's take q equal to what is that, 0.97. I want to take values closer to 1. Okay? I've started fairly close to 1. I will plug in q into each of these summands. There are infinitely many of these summands, and just figure out what value I get. Okay? So this is n is the summand here, and this is the value I get. And you will see that you get a unimodal sequence. So one single peak, and goes like this. And for q equal to 0.97, the peak happens at n equal to 16. So the 16th summand is the biggest, and the value is quite large, it's 10 to the 8. You can do easily on me. Alright? Let's move closer. Q equal to 0.99. Okay? Now the peak moves to the right, and this is not drawn to the scale. You will realize that I cannot draw it to the scale because the height is 10 to the 27. Even on a logarithmic scale, I have to go 3 times as high, right? So it's a big peak and it moves to the right. Okay? So remember, I'm just plotting the summand. So essentially, this sum is the area under this curve. Yes. So I want to know how high the summand is, where it appears. So given a value of q, I want to know how high the summand is, where it appears, and then you have to do a little bit of analysis to figure out what is the distribution and how far it is. And right? Is that clear? Okay. So let's figure out where the peak appears. If you give me a q, this is experimental so far, but at some point you have to do some hard analysis. Okay, so for a fixed q, this is a unimodal sequence of summands. Unimodal means just one peak. So let's figure out where the peak appears. Okay, so the peak will appear roughly when two neighboring summands are the same as each other, right? Derivative equal to 0 in a discrete case. What does that mean? So this is one summand, and I'll now use the factorial notation. So the next is the chalk visible or?
It's visible to me. The camera is mostly seeing it.
Mostly seeing it. This is probably the only part I can explain well. Okay, right? That's n plus first summand is roughly equal to the nth summand. So the ratio is roughly equal to 1, right? Derivative equal to 0. So let's solve it. This is easy. This is q to the n squared plus 2n plus 1 divided by q to the n squared. So on top I'll be left with 2n plus 1, right? And this is like factorials dividing. So only the last term survives, and you get 1 minus q to the n plus 1, and I want that to be approximately 1. Okay? So what does that give me? That q to the 2n plus 1 is approximately equal to 1 minus q to the n plus 1. So let's simplify that. Okay. So q to the 2n plus 1 plus q to the, or that's equal to, sorry. Okay, I have to do one step. So remember, q is going to 1. So q to the 1 is roughly equal to 1. I am taking q to be very, very close to 1. So I can write this is all happening approximately anyway. So I can write this as q to the 2n is approximately equal to 1 minus q to the n, right? Q to the 1 is roughly 1. Okay? So let us put phi to be equal to q to the n. What do I get? Phi squared is 1 minus phi. Okay? That making sense? Okay. What is the phi there? should be related to golden ratio. And remember, Q is very close to 1 but to the left of it, so any power of it will still be within 0 to 1, right? So phi happens to be, let me write it in, okay, so minus b plus or minus under root b squared minus 4ac divided by 2, but I want something that is positive between 0 to 1, so I just say that. So that's related to the golden ratio, right? Okay, so what have we done? For a given q, the peak happens at that value of n, where q to the n is roughly equal to this phi. For a given q, peak happens at that value of n. Okay. Okay, so I have figured out where the peak appears if you give me a q. Now you have to do a little more analysis to figure out exactly what the area is. It's, right? You have to figure out what the distribution is, what the area is, and you are done. And you do that analysis and you see that the most dominant term from the sum sides is of the shape exponential of, I'll tell you what all this means. Divided by epsilon. Yeah, it has to be something divided by epsilon because it has to match what you get from the product side. It's just what is it divided by epsilon. So here there is L. So what is this L? L is what is called the Rogers logarithm function. Okay, what is that? So L of x is x to the n divided by n squared. So normal logarithm just has n, or plus or minus signs, but n, right? This dilogarithm because it's n squared. Okay. Plus, it requires a little bit of a correction to have a good functional equation, like so. Now it's not defined at 1, but you will see that it has a limit at 1 and it's phi squared over 6, this function. This part has limit 0 and this is just 1 over n squared, which is pi squared over 6. Okay? So L of 1 is pi squared over 6. Alright, and L of 0 is 0. That's another limit that it has. So what do you get here? Well, if you compare the most dominant terms, then you get L of 1, which is pi squared over 6, minus L of that equals pi squared over 15. So you massage it a little bit and you see that, okay, is pi squared over 15. Okay. The point of me doing all this was that this dilogarithm function it's very interesting. This is one of the few values for which its evaluation is exactly known. There are like 7 or 8 values for which it is known exactly what it equals. And one of the conditions you usually get for modularity doing this business is that there is certain dilogarithms added or subtracted with some fractions like 1 over 3 or something if you have a cubic bookhammer, and you get various values depending on what quadratic form this is, and they have to evaluate to a rational multiple of pi squared as one of the conditions that is necessary for modularity, and that came about just by looking at the most dominant terms. Okay, right? So this came about by just looking at the most dominant term. Now, if you look at a paper of, 3 minutes. If you look at a paper of Vlasenko and Zwegers from 2011, they do the full analysis. They don't just give the most dominant term, they write down the entire asymptotic expansion, as it's called, and they figure out what it has to be modular, and you get infinitely many constraints. This was just one constraint based on the most dominant term. You have infinitely many terms, you get infinitely many constraints. So you get infinitely many constraints for modularity. Okay? The punchline is, okay, so they didn't consider the general programmers like what I had, cube, 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 cube. They just consider everything to be a cube, but it's very easy to generalize what they did. So the punchline for the talk is, if you implement these infinitely many constraints for the conjectures I gave you, then on the computer it looks like nothing else of that shape satisfies those constraints. But I am not able to prove it, it's just on the computer because the equations are very, very complicated to prove by hand. Okay? So since I still have 3 minutes, I will tell you the analog of this dialogarism identity that comes up for the conjectures I presented. Okay. So this dialogism business is very classical, as I learned. Many people have. And it's also related to tensor categories. So these come up as quantum dimensions of relevant tensor categories. Anyway, so for the KR conjectures, I just mentioned the dialogarism identity that you need to satisfy for the equality rule. It is L of Q1 plus a third L of Q2 cube. So remember I said you get a bunch of terms using dialogarisms and sometimes there are fractions. This fraction comes about because there was a cubic hammer in the denominator. Equals, I don't know if it equals, but on the computer it looks like it is this. You can use the identify command, I guess, on Maple, right? What are Q1 and Q2? They are two algebraic numbers in 0, 1 that satisfy Q1 cubed minus 3 Q1 squared plus 1 equals 0. Q2 to the 9 minus 6 Q2 6 plus 3 Q squared plus 1 equals 0. There is a paper of Loxton from 1984 where he has a similar dialogarism identity. Maybe this one is related to that, and it's easily derivable from that. But anyway, it's still not going to prove the conjectures, but yeah, that's the identity. And that's it.
Let's thank our speaker. Are there questions?
So this is really fascinating. So it's all conjectural and experimental,
Yeah.
but how general will this type of analysis get?
Oh, this you can do for anything. The general form that I wrote down for analytic sumsides with q raised to a quadratic divided by Kokomo. So there is a theorem that tells you what the asymptotic expansion should be. It's just hard to implement and prove anything with it.
Other questions?
If you somehow were able to prove the modularity without using the conjectures, would that help you in proving the conjectures?
Yeah, because usually the space of modular forms is finite dimensional.
Okay, sure.
So you have to figure out, there is some also, I said SL2Z in my definition of modularity, right? But here it's not SL2Z, it's a congruent subgroup that comes up. You just need to make sure that there are finitely many, the space is finite dimensional, and then if it's 60 dimensional, you check for 60 coefficients and you're done,
Sure.
right?
Okay, thanks.
But yeah, I don't, even in the Rogers-Ramanujan case, no one's proved modularity using just the sum sides. That's the open thing.
Any more questions? Let's thank Shashank again.
All right.